This lecture is going to introduce two new thermodynamic properties called specific heats. Now there's two versions of these properties, and we want to clarify what the difference is between them, and hopefully by the end of this lecture we see what their application is. So the first of these two is called the specific heat at constant volume. So first of all, the symbol that we're going to be using for that is a C, and to remind ourselves that we're talking about specific heat at constant volume, we have a lowercase v as a subscript on that. So this is the definition of specific heat at constant volume. Now remember, any thermodynamic property, and CV is just a new one of those, can be expressed as a function of two other thermodynamic properties. Well, CV is defined as a function of U, the internal energy, and T. The definition is that it is the rate of change of U with respect to T. So partial U, partial T is the specific heat. And we typically remind ourselves that we're talking about CV, the specific heat at constant volume, by putting a subscript V on the right-hand side of this equation as well. So specific heat at constant volume is defined like this. Now we're going to see what it's useful for as we go forward here, but right now we're just laying out the definition of it. This second equation over on the right is really exactly the same equation over again. Notice what the difference is. We just have a bar over top of the U, which means that's a molar specific internal energy, and if we have a bar over top of the U, that means there's a bar over top of the C as well. So this equation is on a molar basis, this one is on a mass basis. So the bar means exactly the same thing as it has with other properties. So that's the specific heat at constant volume, partial U, partial T. The other version of specific heat, or the other specific heat that we often make use of, is the specific heat at constant pressure. So that's called CP. And it is defined as partial H, partial T. So the rate of change of enthalpy with respect to temperature at constant pressure. So again, the subscript P is on both sides of this equation as a reminder. And again, there's a molar version of that specific heat, just a bar over top of the H, therefore a bar over top of the C as well. So these are the two versions of specific heat that we're going to be talking about in this lecture. And they're very useful properties for calculating changes in internal energy and enthalpy from changes in temperature. That's their particular use. There's a third property that we'll define at this time, which is directly related to CV and CP, and that is called the ratio of specific heats. The symbol that we'll be using for that is a lowercase k, and it's defined as CP over CV. And we'll see later on how useful this is, but it turns out to be a very useful property for lots of different important processes. So, specific heat at constant volume, specific heat at constant pressure, and the ratio of specific heats. Those are terms we're going to be using quite a bit from now on. Now what we want to do is see what these properties are used for. What this slide shows us is the definition of these three properties, and that definition is the same no matter what substance we're looking at. It could be any substance, it could be at any region of the PVT surface or ideal gases. These definitions are valid. However, these quantities are most useful when we're looking at ideal gases. So the next thing we want to do is look at what happens to these specific heats, or what special properties do they have that make them so useful for ideal gases. So that's what we're going to do next. So we want to look at CV and CP for ideal gases, and in addition to that, we're going to look at U and H as well, the internal energy and the enthalpy. Well, remember our definition of ideal gases. We certainly had the ideal gas law, PV equals RT, but the other part of that was that internal energy and enthalpy were only functions of temperature. So this fact leads us to a simplification of the definition of CV and CP, and we'll see how that works. So remember how we defined CV and CP on the previous slide. partial U partial T is CV, partial H partial T is CP. Well, if this U and this H are only functions of temperature, then we can say this is actually just du dt. Remember what a partial derivative is? That's indicating that you're differentiating this quantity with respect to just one of the variables that it depends on. So in general, this u would be a function of more than one variable. And of course, in general, it's a function of two variables. However, for ideal gases, it's not. It's only a function of one variable. So that means that we can express CV just as du dt and Cp just as dH dt, derivatives of only one variable, temperature, because they only depend on temperature. So this is quite useful because it means we can essentially undo this relationship by integrating it and figure out changes in internal energy from changes in temperature. And that's what CV and Cp are really useful for. Now, the other thing to say here, if U is only a function of temperature, which it is for an ideal gas, and we're taking du dt, that means that CV is only a function of temperature. And of course, same thing for Cp. So CV and Cp are only functions of temperature. Now, the other thing that we're going to do with these expressions is undo them. Okay, so we're interested in using these to calculate changes in internal energy and changes in enthalpy. So that's done on the next slide here. So U2 minus U1 is going to be the integral from 1 to 2 of CV dt. And H2 minus H1 will be the integral from 1 to 2 of Cp dt. And remember, CV and Cp are only functions of temperature. So this is the usefulness of specific heats. They allow us to calculate changes in internal energy and enthalpy from changes in temperature. Now, where do we get these functions from? How do we figure out how that depends on temperature? Well, there's a few different ways to do that. We're going to introduce a couple of them now. The first option that we have is to go and get an equation that tells us how these things vary with temperature. And in fact, that's available in your textbook. If you look at table A21, it gives functions that tell us how CV and Cp vary with temperature. And here's an example of one of those functions from that table. So they're given as polynomials. Okay, so we have, in this case, Cp, and it's actually given as a ratio of Cp over R. So that's a dimensionless number. To get Cp, you'd need to calculate this out and multiply by R. So the table itself gives the value of these coefficients, alpha, beta, gamma, delta, epsilon, for a whole bunch of different gases. And so at any particular temperature, you put the value of the temperature in here in degrees Kelvin, calculate this out, and you get Cp. So notice this is giving Cp as a function of temperature, and it's a polynomial that describes that connection between Cp and temperature. So we could take this equation and put it in here and integrate it and use it to calculate changes in enthalpy. So that's certainly one option. So let's look, however, at several options for calculating delta U and delta H for ideal gases. So one is the one I just talked about. Use equations for Cp given in A21 and integrate them. Notice we would have to integrate them, just going back to this expression here, we would have to evaluate that integral. So if you're doing hand calculations, that's a little bit tedious. This is a fourth order polynomial. It's doable, but it's a little bit tedious. So for hand calculations, this is tedious, but of course it's quite accurate because the fourth order polynomial does a really good job of returning an accurate Cp as a function of temperature. Now, if you look at table A21, you'll notice that it actually only gives information for Cp. So what do you do if you need Cv? Well, this is a very important relationship that we always need to remember. It turns out that Cp minus Cv is equal to the specific gas constant. So what that means is if you know one of these, then you know the other, because presumably you know what gas you're dealing with, so that gives you R. So if you're given either CV or CP, you can always use this expression to get the other one. So table A21 doesn't actually give any information about CV. It relies on you using this to get CV if you need it. Now, the second option for doing this is to use what are called ideal gas tables. And ideal gas tables give U and H directly. So examples of those in your textbook, table A22 for air, and table A23 has that data in it for a variety of 4 or 5 other gases. So we're going to be using particularly table A22, but we'll use A23 a fair bit as well as we go on and do some examples. So these tables are really quite accurate and quite simple to use. And if we're doing hand calculations, they're a very convenient way to go. So most of the time when we're doing hand calculations, which of course we're doing in the context of the course, on assignments and exams, etc., we're going to be using these ideal gas tables to get internal energy and enthalpy. But of course, just like the tables for water properties or refrigerant properties, often we need to interpolate to get the conditions that we're interested in. The third option for calculating delta U and delta H is to assume constant specific heats. So this is letting CP and CV be constant. Now it turns out that CP and CV, although they are functions of temperature, are quite weak functions of temperature. So they don't vary very much over a fairly wide range of temperature. So the advantage of doing this is it gives very, very convenient analytic expressions that connect changes in temperature to changes in internal energy and, of course, enthalpy. So notice, if we're willing to assume that CV and CP are constant, then they can come outside of the integral sign, and the result of this is just CV T2 minus T1 or CP T2 minus T1. So for many problems, this is a really good approximation. And what it really comes down to is, are we looking at a process with a large temperature change or not? If the temperature change is quite moderate, and I would say rule of thumb 100 degrees C or so, then this is going to give very, very accurate results. However, if the temperature change gets significantly larger than that, then CV and CP actually change a fair bit, and we would be more accurate to use ideal gas tables to get U and H directly, or perhaps use the table A21 and integrate the expression for CP as a function of temperature. Now, if you're writing a computer program or building a spreadsheet that is doing calculations, certainly the equation from table A21 is the way to go. However, if you're doing hand calculations, then approach 2 ideal gas tables, or perhaps sometimes assuming specific heats are constant, approach 3 is the way to go. The next thing I want to do is an example. Just illustrate how to calculate changes in U and H for a typical set of conditions here. So this example, the working substance is air, and it's going from 100 kilopascals and 300 Kelvin, so that's our P1 and our T1, we'll call that, to 300 kilopascals and 450 Kelvin. So that's P2 and that's T2. So we're going from state 1 to state 2, and the question is just, what is the change in internal energy and enthalpy? Well, the first thing to realize here, and this is something we want to get used to with ideal gases, this problem statement has given pressure and temperature, so P and T, at both ends of this process. Well, realize that the pressure has nothing to do with this problem. U and H are only functions of temperature for an ideal gas, so the only thing we need to pay attention to is the temperature at the beginning and the temperature at the end. And you want to get used to that. Temperature is what determines U and H. It's not dependent on the pressure. So that's an important thing to remember. We're going to calculate this 2 different ways and just compare the results and see how accurate these different techniques are. First one we're going to do is using ideal gas tables. So this substance is air, and table A22 is an ideal gas specifically for air. So we're going to go to table A22 and get the values of U and H at these two temperatures, 300 Kelvin and 450 Kelvin. So here's a look at table A22 right out of your textbook. Notice here it says ideal gas properties of air. So the two temperatures we're interested in is 300 degrees Kelvin, that's where we start. So here's our value of U and our value of H. You need to be careful using this table because realize that the order that U and H are given in here is different than it is in the property tables for water or refrigerants. So the first column is H, second one is U. The only reason they do that is it turns out H is much more commonly used in the types of calculations that we're going to do, so they just put it in the very first column. But as long as you're careful about that, that's U and H at 300 Kelvin. And at 450 Kelvin, that's over here. So here's our value of U and H at 450 Kelvin. So this technique, it's just a matter of looking up U and H at the initial temperature and the final temperature and subtracting the two. So that's what we're doing here. So here's the values of U and H right off of the table that we were just looking at. And so U2 minus U1 is 108.55, H2 minus H1, 151.61. So that's just subtracting these values from these values. So this is our first technique. That's the answer to this little question for the first way that we're going to do it. The second way that we're going to do this is assuming constant specific heat. So second technique here, assume constant specific heats. Well, we need a value for the specific heat, and there is a table in our textbook that gives us that. So when we get that value, how are we going to use it? Well, this is just reminding us that if we assume constant specific heats, we can calculate delta U from CV delta T, and we can calculate delta H from CP delta T. So where do we get CV and CP in order to be able to do this calculation? That information comes from table A20 in your textbook. So table A20 shows CV and CP as a function of temperature, so it's tabulated as a function of temperature for air and a few other substances. So this actually allows us to see how strongly CV and CP depend on temperature. We can actually look at the variation with temperature in here, and we're actually going to plot that in a moment just to see how significant it is. However, for our purposes, the relevant piece of that table are these rows that go from our starting temperature 300 to our ending temperature 450. And you can see that CV and CP certainly change, but really not by very much. So we're going to try a few different things here. The first value of CV that we're going to try, we're going to calculate delta U here first of all. The first value of CV that we're going to try is this value at our starting temperature at 300, so 0.718. So U2 minus U1 is CV times T2 minus T1, so here's our calculation, 0.718, that first entry in the table at 300 Kelvin, so here it is down here again, and just multiplying it by our temperature change, which was 150, gives 107.7. So I've entered that in this table here. So that's what we get for U2 minus U1 if we were to use this value of CV. Well, notice that the ideal gas table value that we got earlier was 108.55. So these numbers are actually quite close. This approximate value is less than 1% low. So it's really a good approximation, even if we just go in and use the value of CV at the very beginning of this process. Now, of course, we could have chosen a value of CV from any of those temperatures along the way, and this just shows what would have happened if we did that. So we would go from being about 0.78% low if we chose the beginning value of CV to about 1.29% high if we chose the ending value of CV. So really all of these are quite good. So because we're looking at a fairly limited change of temperature here, 150 degrees, so it's getting a little bit significant, but even for a 150-degree change in temperature, we're still very, very low errors, less than 1% low and about 1.3% high here. So quite an accurate technique, even though the temperature changes 150 degrees. Now, in practice, we could actually still do a little bit better than this. We know our starting temperature is 300 and our ending temperature is 450, so why don't we use a value of CV in the middle here? That will give even better results. So let's see how that works. So this information is just, we've already seen that, just have it there for reference. So we could use an average CV over the temperature range. So if you calculate an average CV, so take that one and average them, you get 0.7225. Use that to calculate delta U, and you get this, and that's about 0.26% high. So very, very close, about 0.25% away from the more accurate answer that we get from ideal gas tables. So any of these techniques using constant specific heats for these conditions really give quite acceptable answers. Now I want to show what's going on with this calculation of delta U graphically. So we want to look here at a plot of specific heat on this axis versus temperature. So this is the data that we got out of table A20 plotted. So we're just showing how specific heat at constant volume, so this is CV, varies with temperature. And this just shows its variation. It's going up. But realize that this plot, the vertical axis here, is from 0.7 to 0.75. So it's sort of an expanded axis there. So the change is not as dramatic as it seems on this plot. Well, realize when we're calculating a change in internal energy, that's the integral of CV dt. Well, that's the area underneath this curve, right? We're plotting CV as a function of temperature, so the integral of CV dt is the area under the curve. So remember that we're starting at a temperature of 300 in our example here and going to a temperature of 450. So we're calculating the area under this curve from 300 to 450. So the first time that we did this calculation, assuming constant specific heats, remember that we used the value of CV at the low temperature here. So essentially that first value of U2 minus U1 that we calculated is this gray area. We're using the CV at the low end, multiplying by the change in temperature, 150, and we got that first estimate of U2 minus U1. So that first estimate we made is represented by this gray area. If we were to instead use the highest temperature, so go to our end point, 450, look up the value of CV for it, which is this value, and use that to calculate delta U, then we would get that area. And of course, we would be overestimating our change in internal energy, which is exactly what we saw in the table. If we used an average value of CV, then we're essentially doing this. We're using a value CV at the midpoint and multiplying it by the temperature change. So we're getting a better estimate of the area underneath that curve. Now the actual value, of course, would be the area underneath this curve. So when we use the ideal gas tables, we're actually getting the proper area. We're not estimating it from a simple rectangle like we are when we assume constant specific heats. But as we've seen, for this example, all of those give really quite acceptable results.